universe is expanding. So you run time backwards in your mind's eye. That means that in the past, the distances between the galaxies were smaller, and you can imagine a time when the distances were so small that everything is effectively on top of each other. That implies that our universe had a beginning. There was a day without a yesterday.
Around 13.8 billion years ago, a singularity, an entity of infinite density and gravity, emerged. It rapidly expanded and cooled, leading to the creation of our universe. This event is known as the Big Bang. Yet, pondering such events does not provide definitive answers, but raises even more questions. What existed before the Big Bang? Is there even a concept of before in the universe, given that time itself may have emerged from this primordial explosion? Are we simply the final chapter in an endless cycle of cosmic death and rebirth? The greatest minds of our time have proposed theories, each one as mind-bending as the next. Some suggest the existence of other universes, while others hypothesize a universe that breathes, expanding and collapsing in an infinite cycle. But in a recent interview, famous physicist Brian Cox has answered this question, and what he claims is truly shocking.
What happens if we discover the universe has always existed? Because it might have. We know there's a thing called the Big Bang, but it might have been something that happened in a pre-existing universe. Maybe that's eternal. What does that mean for your sort of picture of a creator?
Let's attempt to make sense of what happened before time itself began. Picture a universe that breathes. It starts at one point, expanding outward, growing for billions of years, then shrinking, drawing everything in. This is the core idea of the oscillating universe theory. According to this model, our universe is merely one phase in an endless cycle of expansion and contraction, an eternal cosmic rhythm with no beginning or end. Each cycle begins with the Big Bang, an explosive moment of creation, followed by a long period of expansion. Over billions of years, this expansion slows down, halts, and eventually reverses. The universe contracts, leading to the Big Crunch. During the Big Bang, galaxies collide, stars are compressed, and all matter and energy are crammed into a singular point of infinite density, much like the singularity that initiated the Big Bang. But this isn't the end. It's just the start of the next cycle. A singularity then explodes in another Big Bang, sparking the next version of the universe. The lifespan of each universe in this model could last billions, even trillions of years, with each Big Bang setting the stage for the next. Fascinating, right? Like a cosmic pendulum swinging back and forth between expansion and contraction, destruction and rebirth of universes throughout time. However, the oscillating universe theory is not without its flaws and criticisms. Many aspects of the universe's expansion, its exact energy composition, and the behavior of gravity on such vast scales are still unclear. Data from the cosmic microwave background seems to suggest that the expansion is accelerating, possibly ruling out the future contraction. But as always, science progresses, and what was once rejected may be revived by new discoveries. Throughout our exploration of space and time, we've always considered our universe to be unique, a solitary bubble in an endless void. But what if we're not alone? What if our universe is just one of countless others, each governed by its own set of physical laws, history, and cycles of birth and death? This is the foundation of the multiverse theory. Imagine a vast ocean of the cosmos, where countless bubbles form and fade. Each bubble represents a universe on its own, and our universe is simply one among many in this cosmic foam. Some of these universes could differ from ours entirely, with their own set of physical constants or even other dimensions. Others might closely resemble ours, possibly even harboring life similar to what we know. What if some of these universes came before ours? Could our Big Bang have been triggered by an interaction with another universe? The concept of the multiverse pushes the boundaries of how we understand our position in the cosmos. However, it remains a highly speculative theory. While the multiverse theory is intriguing, it also stirs controversy. If these other universes exist beyond our reach, how can we detect or study them? And if the theory can't be tested, can it truly be considered scientific? Still, the multiverse theory continues to generate research and debate among physicists. It resides at the frontier of knowledge, where science intertwines with philosophy and the observable world gives way to deep questions about the nature of reality. And yet, despite the existence of these potentially infinite universes with their varying forces and dimensions, let's focus back on the reality of our own. Our current understanding of the universe is grounded in two key pillars of modern physics: quantum mechanics, which explains the world of atoms and subatomic particles, and general relativity, which describes large-scale structures. But what happens when these two worlds collide? Einstein's theory of general relativity tells us that space and time are connected in a four-dimensional fabric known as space-time. Large objects distort this fabric, creating what we perceive as gravity. In contrast, quantum mechanics reveals a world where particles can exist in multiple states at once, disappearing and reappearing in ways that defy everyday logic. These two frameworks intersect at the singularity of the Big Bang and at the core of black holes, where quantum mechanics and gravity meet. For years, scientists have sought a theory of quantum gravity to unify these two views. One fascinating idea that emerged is the no-boundary proposal, developed by physicist Stephen Hawking and James Hartley. According to this theory, the universe didn't originate from a singularity. Instead, space and time are finite yet boundless, much like the surface of the Earth. Just as you can travel the Earth's surface without falling off, you can move through the universe without encountering an edge. The universe would be a four-dimensional sphere, with the Big Bang acting as a smooth point, much like Earth's North Pole, but not a singularity. In this model, asking what happened before the Big Bang is as meaningless as asking, what's north of the North Pole? This offers an interesting way to bypass the singularity issue at the universe's origin. Like many other theories we've explored, the no-boundary proposal is still being scrutinized and researched. However, it provides a compelling approach to uniting the vastly different scales of the incredibly large and the incredibly small, pushing the limits of our understanding about the universe's beginnings. Now, let's consider string theory, a theoretical framework where the basic components of the universe are not particles, but one-dimensional objects called strings. Each string vibrates at different frequencies, and these different vibrations correspond to different particles, electrons, quarks, photons, all seen as strings resonating at various notes. But string theory goes further. It also suggests there are more than the three spatial dimensions we experience. These additional dimensions may be compacted or hidden from us, but they still play a crucial role in shaping the very fabric of reality. In relation to our discussion, one version of string theory, known as the pre-Big Bang scenario or the ekpyrotic model, proposes that our universe might have originated from the cataclysmic collision between two multiverse worlds, or branes. So, what happens following such a collision? The two branes would bounce off one another, only to be drawn back together by gravity, colliding again billions of years later, possibly leading to the creation of another universe. Now, what existed before the Big Bang? In this model, it's possible that another universe, similar to ours, could have existed on a brane parallel to our own. However, while string theory is elegant and successfully unites quantum mechanics with gravity, it lacks empirical evidence. As we know, proving such ideas can be extremely challenging. But what if we take a different route? Rather than seeking a universe that came before ours, what if we reconsider the very concept of nothingness? When we think of a vacuum, we often picture absolute emptiness. But in the quantum world, the vacuum is far from being empty. It's a dynamic space where particles and antiparticles constantly pop in and out of existence, only to annihilate each other. This phenomenon is known as vacuum fluctuations. The vacuum fluctuation model, or the quantum fluctuation model, posits that our universe could have originated from one of these fluctuations. A minuscule bubble of false vacuum could have inflated into the universe we know, driven by quantum mechanics. This bubble, through phase transitions or quantum tunneling, would rapidly expand, with its edges pushed outward by negative pressure. Within this bubble, false vacuum energy could transform into matter, eventually giving rise to stars, galaxies, and everything else, including us. So, what was there before the Big Bang? According to the vacuum fluctuation model, it could have been a quantum vacuum, filled with fleeting particles and antiparticles. Our universe was simply one random bubble that managed to grow into something much larger. While the vacuum fluctuation model presents an intriguing possibility, it also raises challenging questions. For instance, why did this particular bubble expand while others did not? And how do we explain the existence of an eternal quantum vacuum in light of the universe's apparent age? As we explore further into quantum physics, we encounter more fascinating possibilities. One such concept is a theory that combines quantum mechanics and cosmology, leading us to the Big Bounce theory. Imagine a universe that expands, contracts, and then rebounds elastically. That's the core idea behind the Big Bounce theory. Instead of a singularity, where the laws of physics break down, the Big Bounce theory suggests that our universe may have arisen from the remnants of a previous contracting universe. In this model, the universe doesn't collapse into a singularity. Due to quantum effects, it compresses to a small size before expanding once again, giving rise to what we perceive as the Big Bang. This theory, similar to the oscillating universe theory, suggests that the universe has no true beginning or end, but follows an endless cycle of expansion, contraction, and renewal. The Big Bounce theory addresses issues in other models by avoiding their singularities. Unlike the oscillating universe theory, it focuses on the specific point of transition, the bounce between contraction and expansion. Quantum mechanics plays a role here on the very small scales involved in the rebound process. Quantum theory suggests that particles can tunnel through barriers, even when they don't have the classical energy needed to do so. Some theories propose that the universe might use a similar quantum tunneling effect to transition from a contracting state to an expanding one. However, this remains highly speculative and faces significant challenges, both theoretical and observational. One of the questions is whether we can find evidence of a contraction phase in the present universe or develop a quantum theory of gravity that can handle these extreme conditions. Despite these challenges, the Big Bounce theory faces significant problems in explaining how the shrinking universe could return to a normal state. Understanding how this might occur without violating known laws of physics is a key obstacle. Additionally, the Big Bounce theory doesn't fully fit within our traditional concepts of time and causality. But as in all areas of science, there are competing ideas. For instance, it's suggested that our universe might have originated from a black hole. Black holes, formed by the collapse of massive stars, are regions where gravity is so intense that nothing, not even light, can escape. The core of a black hole, according to general relativity, is a singularity, where density becomes infinite and space-time curvature reaches extreme levels. But some physicists suggest that these singularities could give rise to new expanding universes. meaning our universe could be inside a black hole from another universe. In this view, the Big Bang would correspond to the formation of a black hole singularity in the parent universe, and the expansion of our universe would mirror the internal growth of the black hole. This leads to the question, what existed before the Big Bang? It could be the interior of a black hole from another universe, with every black hole in our universe potentially creating a new universe inside itself. While this is an intriguing idea, it's still a hypothesis with its own problems. How could we test this theory? How would we observe effects from the parent universe? And how can we reconcile this with our current understanding of black holes and singularities? Loop quantum gravity, or LQG, is a theoretical framework that aims to bring together two major pillars of 20th century physics: quantum mechanics, which deals with the smallest scales, and general relativity, which governs the large-scale structure of the universe. According to loop quantum gravity, space is not continuous as traditionally thought, but is made up of tiny, discrete loops. These loops are indivisible, much like how fabric is made up of interwoven threads. When applied to cosmology, loop quantum gravity, or more specifically loop quantum cosmology, proposes a rebound scenario, which is quite similar to the Big Bounce concept we explored earlier. In fact, loop quantum cosmology offers a detailed quantum mechanical description of the universe's evolution, incorporating the Big Bounce idea. Rather than collapsing into a singularity, as traditional Big Bang theory and general relativity suggest, the universe contracts to a minimum size. However, quantum gravitational effects take over and prevent further contraction. At this point, the universe bounces back and begins expanding once again. This implies that our universe might have gone through numerous cycles of expansion and contraction, each marked by a quantum leap. So, what existed before the Big Bang? From the standpoint of loop quantum cosmology, it could have been another phase of the universe, what we might call the contraction phase, which came before the quantum jump. An intriguing aspect of loop quantum cosmology is the concept of a quantum bridge. This bridge marks a transitional phase that connects our universe to the one that came before it. Instead of a singularity, the universe undergoes a quantum leap and begins to expand. This shift from contraction to expansion can be viewed as a quantum bridge between the previous universe and the new one. This quantum bridge isn't a physical bridge, as we typically think of it, but rather a stage in the universe's evolution controlled by quantum gravity. So, what lies beyond the Big Bang? According to loop quantum cosmology, the prior universe is connected to ours through a quantum bridge. Although this theory removes the singularity from the Big Bang and provides a coherent quantum description of the universe's evolution, it still faces significant challenges. Even so, if the theory holds, it paints an incredible picture. A universe with no true beginning or end, experiencing infinite cycles of contraction, quantum leaps, and expansion. While these theories present fascinating possibilities, most of them remain speculative at this point. Each theory has its own set of strengths and weaknesses, and none has definitive experimental evidence to support it just yet. As we move closer to understanding what came before the Big Bang, it's likely that each answer will lead to more questions. But that is the true beauty of science, the journey of exploration and discovery. Scientists across the globe continue to study these theories and refine their models, and even focusing on a single theory helps advance our overall understanding. This search is not just about finding definitive answers, but about understanding the very fabric of the universe itself. With each new theory, model, and discovery, we edge closer to uncovering the nature of existence and the forces that shape it. While no single theory currently holds all the answers, they all offer unique insights that may eventually converge into a more complete understanding of the cosmos. One of the most fascinating aspects of this journey is the exploration of the unknown. The vastness of space and the complexities of the laws governing it remain, for the most part, a mystery. Yet, as human curiosity drives us to push the boundaries of our knowledge, we find ourselves on the brink of making discoveries that could redefine how we perceive time, space, and even the origins of the universe itself. The ongoing research into quantum mechanics, general relativity, and cosmology continues to shape our understanding. One of the key challenges scientists face is reconciling these two seemingly incompatible theories: quantum mechanics, which governs the behavior of particles at the smallest scales, and general relativity, which explains the force of gravity at the largest scales, have both proven successful in their respective domains. However, when it comes to describing phenomena like black holes and the Big Bang, both theories seem to break down. This is why the search for a unified theory, such as quantum gravity, is so important. By combining the best aspects of both quantum mechanics and general relativity, we may one day be able to explain how the universe behaves at every scale. Brian Cox, a well-known physicist, discusses the idea of what existed before the Big Bang in a way that's easy to follow. He points out that the question itself may not make sense because time itself began with the Big Bang. This means there wasn't before in the way we usually think of it. According to Cox, time and space as we know them didn't exist before the Big Bang, so it's hard to say what came before it, if anything. In his talks and writings, especially in his book Wonders of the Universe, Cox explains that the universe might have been in a different state before the Big Bang, one that we can't fully understand with our current science. The laws of physics, which usually help explain how things work, break down under the extreme conditions at the moment of the Big Bang. This makes it difficult to apply what we know about the universe to explain what happened before it started expanding. Cox doesn't claim to have a clear answer, but he suggests that science is always evolving, and new theories may emerge over time. While we might not know for sure what existed before the Big Bang, the search for answers is what drives scientific discovery. He encourages people to stay open to new ideas and to keep exploring, even when faced with questions that challenge what we already understand about the universe. So, what are your thoughts on this? Let us know in the comments below and subscribe to our channel for more content.